The Clausius-Clapeyron equation is a powerful tool in chemistry. Meteorologists use it to better understand water vapor relationships in the atmosphere that drive our daily weather, and chemists use it to predict thermodynamic relationships for liquids and solids that can help us better understand how different substances will react to varying temperature and pressure conditions. The Clausius-Clapeyron equation describes the relationship between the vapor pressure of a liquid and temperature. As a reminder, vapor pressure is the pressure exerted by a gas in a closed container when it is in dynamic equilibrium with its liquid. Another way of stating this is that it's a measure of the maximum amount of the gas phase of a substance that can be found above its liquid at a given temperature. The higher the temperature, the more molecules that can escape from a liquid and enter the gas phase. The curved lines for each liquid on this graph show that vapor pressure increases exponentially for every temperature increase. The first form of the Clausius-Clapeyron equation we'll look at directly reflects this exponential nature. In this equation, the variable P represents the vapor pressure of a pure liquid. The Greek letter beta is a constant that depends on the identity of the liquid. E is Euler's constant, which you may remember encountering in algebra class. The expression in parentheses is actually the exponent portion of the equation. The base E is raised to whatever value this expression gives us. Inside these parentheses, delta H vap represents the enthalpy or heat of vaporization in units of joules per mole. R is the ideal gas constant. We use a slightly different form of the ideal gas constant than you may have used last semester. When R is converted into units of joules per Kelvin per mole, its value is 8.314. Finally, T represents temperature in units of Kelvin. The Clausius-Clapeyron equation is much easier to work with when it is not in exponential form, however. In this class, we'll actually work with two variations of the linear form of the equation. I'll show you the derivation of the linear form here because it's a good reminder of the type of algebra you'll be working with this semester. You will not be required to do this derivation again, however. First, we get rid of any exponent to the base e by taking a natural logarithm. If we apply a natural logarithm to one side, we have to apply it to the other as well. Remember that taking a logarithm of two values multiplied by each other is the same as the logarithm of the first value plus the logarithm of the second value. We can apply this situation to our constant beta multiplied by the base e raised to the expression in parentheses. When we do this, it yields the following. The natural log of vapor pressure equals the natural log of the constant beta plus the natural log of the base E raised to the power of the negative of the enthalpy of vaporization divided by R divided by T. The second expression that we need to remember is that the natural logarithm of E raised to any exponent x is simply x. In our equation, x is represented by the expression in parentheses. When we apply the natural log to e raised to this expression, it allows us to eliminate the base e and get that expression out of the exponent. Now we have the natural log of pressure equals the natural log of beta plus the negative of enthalpy of vaporization divided by R divided by T. A simple rearrangement of the two terms on the right side of this equation yields the following. The natural log of vapor pressure equals the negative of the enthalpy of vaporization divided by R times 1 over temperature plus the natural log of beta. The enthalpy of vaporization divided by both R and T is the same as the enthalpy divided by R and multiplied by 1 over T. We rearrange the terms so they allow us to mirror the slope and y-intercept conventions of the standard equation of a line, as you'll see in the next slide. The standard form for the equation of a straight line is y equals mx plus b, where m equals the slope and b equals the y-intercept. In our rearranged form of the Clausius-Clapeyron equation, y is the natural log of vapor pressure, x is the inverse of temperature in Kelvin, or 1 over t. Our slope is m, which is the negative of the enthalpy of vaporization divided by the ideal gas constant R, and the y-intercept b is equal to the natural log of beta. The most common way to use this version of the Clausius-Clapeyron equation is with a graphical analysis of experimental data of temperature and vapor pressure to determine the enthalpy of vaporization. For example, in a laboratory experiment, the vapor pressure of carbon tetrachloride was measured at 6 different temperatures. The data is given in this table. In order to use the linear equation form of the Clausius-Clapeyron equation, we first must transform our data into the appropriate form for the equation. This means that we take the inverse of each temperature point and the natural log of each vapor pressure. These last two columns are what we plot on a graph, with the inverse temperatures on the x-axis and the natural log of pressure on the y-axis. This is what the graph looks like. Each line of data is plotted as a point on the chart. A linear regression analysis can then be applied to this data series. I used Excel to insert a linear trend line and determine the best fit equation for this data. You can also use a graphing calculator to do this linear regression analysis. According to the linear form of the Clausius-Clapeyron equation, the slope of the line is equal to the negative of the enthalpy of vaporization divided by the ideal gas constant, R. We can set the slope calculated during the linear regression, negative 4063.9 Kelvin, equal to the negative of the enthalpy of vaporization divided by the ideal gas constant R, or 8.314 joules per mole Kelvin. We can then rearrange to solve for the enthalpy of vaporization by multiplying both sides by 8.314. This gives us 33,787 joules per mole, or 33.8 kilojoules per mole. Each mole of carbon tetrachloride that goes from the liquid to the vapor phase must absorb 33.8 kilojoules of heat. In this way, we've solved for the enthalpy of vaporization for carbon tetrachloride. We can also use this linear regression to calculate the constant beta for the liquid. Remember that the y-intercept is equal to the natural log of beta. We can set this equal to 18.373, the y-intercept from our linear regression equation. To eliminate the natural log in this equation, we simply raise both sides to the base e. This will eliminate the natural log on the right-hand side and return just beta. So we have beta equals e raised to the 18.373 power, or 9.53 times 10 to the 7th. We use the units torr to match the pressure units for our y-intercept. Another useful form of the Clausius-Clapeyron equation is the two-point form. The two-point form does not require graphical analysis. It's a rearrangement of the slope formula for a straight line. The slope of a straight line is equal to the change in y over the change in x. If only two data points are used, this becomes y2 minus y1 divided by x2 minus x1. In the linear form of the Clausius-Clapeyron equation, y is the natural log of vapor pressure, while x is the inverse of temperature. Slope is the negative of the enthalpy of vaporization divided by R. Rearranging terms and simplifying the natural logs gives the final two-point form of the Clausius-Clapeyron equation outlined in red. The natural log of P2 divided by P1 is equal to the negative of the enthalpy of vaporization divided by R times the difference in inverse of temperature, 1 over T2 minus 1 over T1. Here's an example of a type of problem that requires the use of the two-point form of the Clausius-Clapeyron equation. The vapor pressure of ethanol is 1.00 times 10 to the second millimeters of mercury at 34.9 degrees Celsius. What is its vapor pressure at 55.8 degrees Celsius if the enthalpy of vaporization for ethanol is 39.3 kilojoules per mole? In this problem, we're given one complete data point of temperature and pressure, 1.00 times 10 to the second millimeters of mercury at 34.9 degrees Celsius. We're also given the enthalpy of vaporization, and we're given a partial data point for the second, 55.8 degrees Celsius, and asked to solve for the pressure associated with this temperature. The key to solving this problem is correctly identifying all the variables and making sure they are in the correct units. I'm going to label the first temperature and pressure combination as P1 and T1. Pressure can stay in units of millimeters of mercury, but all temperature must be converted to Kelvin. To do this, we add 273.15 to our Celsius temperature to give us 308.05 Kelvin. The enthalpy of vaporization is 39.3 kilojoules per mole. The correct units for enthalpy in this equation are joules per mole, so we must convert from kilojoules to joules before plugging this number into the equation. R is the ideal gas constant. We always use 8.314 joules per mole Kelvin for this particular equation. T2 must be the second temperature, 55.8 degrees Celsius, or 328.95 Kelvin. We are solving for the vapor pressure P2 at this temperature. We substitute all these values into the two-point form of the Clausius-Clapeyron equation and rearrange to solve for P2. Here's the two-point form equation with these values substituted in. The right-hand side of the equation can be simplified. Plugging into your calculator yields 0.9749396 for the right-hand side. This type of calculation is particularly sensitive to rounding error. I'm carrying several more significant figures to minimize this. I'll round my final answer, but not anywhere in between. Now I need to get rid of the natural log function on the left-hand side of the equation. Remember that raising a natural log as an exponent to the base e essentially eliminates the natural log and leaves us with the value inside. You must raise both sides to the base e, however, to maintain the two sides as equal. The left-hand side raised to the base e simply eliminates the natural log. On the right-hand side, e raised to the 0.974936 power can be calculated using your calculator. This calculation gives us the following simpler equation. We can isolate P2 by multiplying both sides by 100 millimeters of mercury. It cancels out the denominator on the right-hand side and gives us 265.1007 millimeters of mercury on the left. We can now round our final answer to the correct number of significant figures. Each of our original values in the problem had 3 significant figures, so we'll round our answer to 3 significant figures as well, or 265 millimeters of mercury. To summarize, the Clausius-Clapeyron is a powerful equation that relates vapor pressure of a liquid to temperature. There are several forms, but the two most useful to us for calculations are the linear form and the two-point form. The linear form is used with graphical analysis of multiple experimental data points to determine enthalpy of vaporization and the constant beta. The two-point form is used with only 2 data points to find an unknown temperature or vapor pressure.